Inside every single one of us, there's this incredible biological machine. It's working around the clock, 24/7, pulling off this amazing balancing act. And today, we're going to dive into exactly how it performs one of its most unbelievable tricks. Well, it really all comes down to your kidneys. I mean, think about it. Whether you've been sweating like crazy on a hot day, or maybe you just downed a giant bottle of water, your kidneys are constantly making decisions, deciding whether to hold on to every last drop or to flush out all the extra. And the way they do it? Oh, it's nothing short of genius. All right, so here's our game plan. We're going to follow the whole process from start to finish. We'll kick things off with the kidney's main mission, then we'll break down the 3 key systems it uses to build up, power up, and protect a very special environment. And then we'll see how it all comes together to create super concentrated urine.
Okay, let's get right into it. Before we dig into the nuts and bolts of how this works, we really need to understand the why. What's the big problem that the kidney is trying to solve here?
It is all about balance. And just look at this incredible range. When you're dehydrated, your kidneys can crank out urine that is ridiculously concentrated. We're talking up to 1,400 milliosmoles per liter. That's basically just a fancy way of measuring how salty it is. They do this to save every bit of water. But on the flip side, when you've got too much water, they can totally switch gears and make urine that's extremely diluted, as low as 50 milliosmoles per liter. That incredible flexibility is literally what keeps us alive. So to pull this off, the kidney uses millions of these tiny little factories called nephrons. That's what you're seeing on the left. But the real magic, the secret sauce, happens in the space around these nephrons. If you look at the diagram on the right, you can see the kidney builds this incredibly powerful salt gradient. It starts out pretty normal on the outside, in the cortex, but as you go deeper and deeper into the medulla, it gets insanely salty. And that, right there, is the #1 goal. Creating this super salty environment, or if you want to get technical, a high osmolarity medullary interstitium, is the kidney's secret weapon. This gradient is what gives it the power to literally pull water back into the body whenever it needs to. So the big question is, how does the kidney build this salty world and, just as importantly, keep it that way? Well, it's got a team of 3 brilliant interconnected players: the countercurrent multiplier, urea recycling, and the vasa recta exchanger. Let's meet them one by one. First up, we've got the main engine of this whole operation, the countercurrent multiplier. This is the heavy lifter, the process that burns energy to lay the foundation for everything that's about to happen. So what exactly is it? Well, countercurrent multiplication is this super clever process that takes advantage of the fact that you have fluid flowing in opposite directions right next to each other. As we're about to see, the kidney uses this setup in the U-shaped loop of Henle to actively build that powerful salt gradient deep in the medulla. Okay, let's watch this thing in action. It all kicks off right here in what's called the thick ascending limb of the loop. This part of the tube is actively pumping salt out into the space around it. Now, here's the crucial part. This section of the tube is totally waterproof. Salt gets pumped out, but water is stuck inside. It can't follow. So because we just made the outside world salt here, something has to happen. Over on the other side of the loop, the descending limb, the walls are super permeable to water, and by simple osmosis, water just can't help itself. It flows out of the tube to try and even things out. And what does that do? It makes the fluid left inside the tube way more concentrated. But remember, this is a dynamic system. There's a constant stream of new fluid coming into the nephron. This flow acts like a piston, pushing that newly concentrated stuff we just made further down, around the U-turn at the bottom, and toward the ascending limb where the pumps are. And this, right here, is where the multiplication magic happens. This whole cycle, pumping salt out, water following, new fluid pushing it along, it just repeats over and over and over. Every single cycle makes the fluid at the bottom of the loop just a little bit saltier. This allows the pump to then create an even saltier environment outside. It's an amazing example of how a small, local action gets multiplied into this massive vertical gradient, getting all the way up to 1,200 millimoles per liter deep inside the medulla. Now, that salt gradient is seriously powerful. But believe it or not, it's not the whole story. The kidney has another trick up its sleeve to make things even more concentrated in the deepest part of the medulla. And what's wild is that it does this by recycling a waste product, urea. Yeah, I know, you probably think of urea as just trash the body wants to get rid of, but in here, it plays a starring role. The kidney is super resourceful.
It traps and recycles urea, and as you can see, uses it to account for about half of the saltiness in the deep inner medulla.
Let's trace its journey. It's pretty cool. First, as fluid goes down the collecting duct, water leaves, which makes the urea inside more and more concentrated. Then, once it gets deep into the medulla, a hormone called ADH opens up these special urea doors, letting it escape into the surrounding tissue, making it even saltier. From there, it actually diffuses back into the loop of Henle and gets sent around the system all over again. It gets trapped in this inner loop, just adding more and more power to that osmotic gradient.
Okay, so we've put in all this work to build this incredible salt in urea gradient, but that creates a huge new problem. The cells living deep in the medulla, they're alive. They need oxygen, they need nutrients, they need blood flow. So how in the world do you get blood down there without just washing away all that saltiness you worked so hard to create?
Well, the solution is just beautiful. If you had a normal, straight blood vessel flowing through, like on the left, it would act like a fire hose. It would just soak up all the salt and carry it away, completely destroying the gradient. But the kidney uses these very special U-shaped blood vessels called the vasa recta, which you see on the right. And that U-shape, that shape is everything.
These vasa recta act as what we call passive countercurrent exchangers. It's brilliant. As blood flows down deep into the salty medulla, salt naturally moves in and water moves out. But then, as the blood loops back up toward the less salty region, the exact opposite happens. Salt moves back out into the medulla and water moves back in. The net result? The blood can deliver oxygen and nutrients to the cells without stealing a significant amount of salt. It perfectly preserves the gradient. It's amazing.
Okay, all the hard work is done. We've used the multiplier to build the gradient, we used urea recycling to boost it, and we have the vasa recta standing guard to preserve it. Now, it is time for the big payoff. To make the final product, that super concentrated urine, the body just needs two things. First, you need high levels of a hormone called ADH, which your brain releases when you're dehydrated. And second, you need that high medullary osmotic gradient that we just spent all this time so carefully building. ADH is basically the final key that unlocks the whole thing. When it's released, it travels to the very last sections of the nephron, and it tells them to install these special little water channels, called aquaporins, into their walls. It essentially opens the floodgates for water to leave.
And here it is, the grand finale. With those water gates now wide open, the fluid makes its final journey down through that incredibly salty environment we created. And that powerful gradient does all the work, effortlessly pulling water out of the duct and back into the body where it's needed, leaving behind just the waste products in a very small, very concentrated volume of urine.
It's just a beautiful, perfectly tuned system, isn't it? Working nonstop, keeping us hydrated and healthy, but it does bring up a really critical question. This intricate, microscopic dance of pumps and channels and flows is absolutely essential for our lives. So what happens? What are the devastating consequences when any part of this amazing machine starts